Okay, guys, so this is the second lecture of the electricity unit. We are on the voltage, current, resistance lecture, so go ahead and make sure you have that out, either printed or up on Notability and watching the video on a separate device. All right, so here we go. We're going to start with electric potential. Okay, electric potential is measured in units of volts. Okay, so sometimes we call this voltage. Usually that's the word you're going to hear rather than electric potential. Okay. Basically, electric potential or voltage is the source of the electric potential energy in a circuit. So this is what gives the circuit energy. This is why the current flows, because it has this potential difference. Positive charges move towards lower electric potential, and negative charges move toward higher electric potential. This example, this problem right here, we're going to talk about in class. Okay, so just make a note. We're going to talk about that in class at the beginning of next class. All right, I want to get to the analogy, and I want to keep the video short. Hold on one second. Okay. All right, so electric current we use the letter I, okay, and essentially electric current is the amount of charge that passes through some given area per second. So it might help to think about this as like a pipe of water, and as the water flows through the pipe, the more drops of water that pass through the pipe each second, the more current there is. Okay, so the more charge that passes through a given area per second, the more current there is. So as it would with a pipe, if you make the pipe wider or you add pressure to the current or add pressure to the water, that would change the current flowing through it. The equation we use for current is I. I is the variable for current. I know that's weird, doesn't make a lot of sense, but we've already used C for other things. Is the amount of charge, remember Q, per unit time. Okay, and the units that we're going to use are going to be essentially coulombs per second, but we don't use that, we use amps. Okay, and we use a capital A. Okay. For voltage, up here we're using V as the variable. And I know this is confusing, but we measure it in volts, and so it's also V for the voltage as the unit. Okay, so real quick, we'll do this example really fast just because this is pretty simple. The current in a light bulb is 0.835 A, so that's the I, that's the current, and it's in amps. How long does it take for a total charge, so your charge is given to you as 1.67 coulombs, to pass through the bulb, and we're looking for T. So you just simply plug it in to the given equation and solve for T. And your result is 2 seconds. Okay, so hopefully that was pretty easy for you. Resistance is our third variable. So we have three variables. We have, let me just write these over here. We have R, resistance, I, current, and V, voltage. Okay, sorry about that. Let me widen this camera view a little bit. Okay. And so resistance is in opposition to electric current. Okay, it tries to slow the current down. This could be anything like a light bulb or anything else you plug into the circuit. Those things all slow the current down. Okay, so that's the resistance. We measure resistance in ohms. Okay, spelled like that, and we use this weird variable for resistance for ohms. Okay, it's omega ohms, omega, okay? The equation that we're going to use to relate these three variables is called Ohm's law, and the equation is V equals I times R. Super simple looking equation. We're going to use this a ton. You will end up memorizing that equation, okay? And we have ohms for resistance, we have V for volts, and we have A for amps. Okay. Now, in the next part of the video, I'm going to go through an analogy for solving circuits that I hope will help you guys to understand it. And so what I'm going to do is I'm going to go to a blank sheet of paper, and I think you guys should do the same thing so that you have enough room. So go ahead and get that separate sheet. Okay, so here's the idea. We call it the cookie analogy. Okay, so I'm going to have you draw a quick little setup of this little town. Okay, so we have a little house down here. Okay, and up here we have a cookie factory. Okay, and this is the road from the factory to the house, okay? This is going to be like our battery, okay? And this is going to act as our resistor. So in this case, we can kind of consider it like a light bulb, okay? But that's a resistor. And then along this road, we have little trucks that are leaving the factory, and they leave the factory, every single truck leaves the factory with 3 cookies, okay? It's either a really big cookie or a really small truck, whatever you want to think about it. If this truck leaves with 3 cookies, and the next truck leaves with 3 cookies, and the next truck leaves with 3 cookies, that means that this is a 3-volt battery or a 3-volt factory, okay? So we put 3V next to it. When they leave the factory, they leave from the positive side because they have positive cookies in the trucks. And when they come back to the factory, they are going to come back with 0 cookies, okay? They're going to take the cookies and they're going to deliver them to the house. There are multiple trucks. As you can imagine, 3 cookies is not enough, so there are multiple trucks on the road, okay? The trucks are going to be, sorry about that. The number of trucks per second is going to be our current. Okay, number of trucks per second is going to be equal or similar to our current. Okay, our number of cookies per truck that comes out of the factory, that's the voltage. Okay, and the resistor is the number of basically how much this slows down. Okay, we're going to solve for that. Okay, now, well, we can solve for any of these things. Now, if you can imagine a person that was standing here watching the trucks, okay, and they're all passing by, the number of trucks he sees per second, that's going to give us the current, okay. Now, every time a truck goes into this house, because there's only one house, it will go in with 3 cookies, okay, and it will come out with no cookies. Okay, and every single time the truck comes by, it leaves 3 cookies and continues back to the factory. Okay, now because there's only one house and because the house takes all the cookies and because this has to come back empty, that means that this house is a -3-volt house, meaning that it basically has a potential difference or an electric potential or a voltage drop, we call that a voltage drop, of -3 volts, okay? And what we could do is we could say that we're seeing maybe, 10, let's say that our I is 10 trucks per second, so it'd be 10 amps, and we know our factory is 3 volts, so our voltage is 3 volts, and you could solve for the resistance using your Ohm's law, right? So if our voltage is 3 and our I is 10, then we can solve and we would know that our resistance in this house is 3/10 or 0.3 ohms. Does that make sense? So hopefully you can kind of see that analogy, okay? Now this is a very simple basic circuit, okay? And a lot of times there are more than one house, so we're going to jump to that idea. Okay, now we're first going to deal with series resistors, okay? And the series resistors means that they are all along the same line here. We'll compare it with parallel resistors, but for now, these are series resistors, ones where the trucks have to pass by every single house to come back around and get back to the factory. Okay, so these 3 resistors are in series. So go ahead and pause the video real quick and draw this picture. Okay, and so here's the idea. If we have the trucks and they're coming along this road, every single truck has to go to every single house, okay? And so what happens is we have each truck will come by, and every time a truck comes by, because there are 3 houses, it's going to drop 1 cookie here, 1 cookie here, 1 cookie here, so that by the time it ends up on the other side, the truck has no more cookies so that it can go back to the factory. So we would say that each one of these houses has a -1 volt voltage drop. Whoops. Okay, -1 voltage drop. Okay, and if we were to add the resistors up to look at it as one resistor, we would say that we would just add them in series, meaning that we would just add them like normal. So the total resistance of this circuit would be R1 plus R2 plus R3. You can label these 1, 2, 3. Okay, and that would give us our total resistance. If you wanted just the resistance on one of these, you would just take the current, right? So the number of trucks per second, and you would use V equals IR, and you would know that the voltage across one of these houses was -1 or 1, and you would plug in the current and you would solve for the resistance. Okay. In order to find the current, if you're given the resistance, you could just use the same thing. You'd have to combine them all together, and then you could find the current. So I want to kind of go through what that would look like. So if this were a 10 ohm resistor, and this were a 10 ohm resistor, so they're the same, and this were a 20 ohm resistor, okay, then what would happen is we would add all of those up to find the current. So we'd add them all up in series, so it'd be 10 plus 10 plus 20. And so we'd get a total resistance of 40 ohms, okay? And we know that our V total is 3 because it says that's what's happening at the factory. And so we could use V equals IR to find the current. Now the current, or the number of trucks per second, has to be the same in every single house, okay? And the reason for that is that these trucks cannot get off the road. They have to go by every single house, and they can't leave all the cookies at one house and then stop at the next two and be empty, okay? So if these are different, then the voltage drop across them is going to be different. But the current will remain the same. So the I is going to be 0.075 amps, and then if I wanted to find, that's the total I, but we know that the current has to be the same in all three. So for a series circuit, the current is the same in all three, but the voltage will be different if the resistance is different. So we would just take this I, we'd multiply it by 10, and so each one of these would be 0.75 volts voltage drop, right? And then this one would have to be 0.075 times 20, and so it would get 1.5 cookies, where these two would only get 3/4 of a cookie at each of their houses. Okay, so that's series. We're going to now move to parallel. All right, so this is going to be parallel. Okay. All right, so for parallel circuits, this is how it's set up, okay? So you have to imagine that the houses are on different streets now. In the series circuit, you were imagining the houses all on the same street. Now they are on different streets, okay? So that's the definition of them being parallel. So again, we have our 3-volt factory. It's going to spit out trucks that have 3 cookies in them, and the truck is going to go by and deliver the cookies to a house. Now, because they're on 3 different streets, the truck is only allowed to go in one direction. So he can go this way and he can cross through the middle house, he can go this way and cross through the upper house, or he can go this way and cross through the lower house, but he can't go to all 3 houses. So different trucks will go to different houses. The way that they split up and the number of trucks that go to each house is dependent on how resistant the houses are. So in this situation, I have 10 ohms, 10 ohms, 10 ohms. So these are the same resistors, and so you'll get an even number of trucks to each of the houses. Okay, and each house will get all 3 cookies because the truck can only go to one house. So he has to drop off all cookies at one house. So that means that each of these is a -3-volt drop. So the voltage across a parallel circuit is the same. Just like the current was the same in the series circuit, now the voltage is the same in the parallel circuit. So it's just opposite, okay? Now, because these are the same resistance, the number of trucks that go by each, right, will be the same because these are the same resistance. But if we were to change that, okay, if we were to change this and we made this house 20 ohms, okay, then the number of trucks that go by this house will be different than goes by these 2 houses. The way that we combine resistors here in order to find the total current coming out of the factory, we need to know the number of trucks coming out before we can figure out how many go in each place. In order to find the total number of trucks, we have to add up the resistors. Parallel resistors add up much differently. So when we add a parallel resistor, we say that R total, or 1 over